If I drop plywood in water, it will float 100% of the time. If I heat water to 100 degrees Celsius in a standard atmosphere, it will boil every time. If I cool water from 80 degrees to 34 degrees Fahrenheit, the water will expand at 34 degrees as it approaches it every time, and by a known amount. Assuming good working order and lubrication, if a spark plug ignites fuel in an engine cylinder, it will cause the cylinder to move every time. If moist air is cooled to its dew point temperature, dew will form every time. The problem with physics and physics laws are, for this, what we're going to talk about here, the Coriolis effect, is there are no exceptions to the rule. If this is what causes low pressure systems to spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, because the wind at the equator is moving faster, or the Earth rather is spinning faster at the equator than it is at other latitudes, like in this picture. At some northern latitude and some southern latitude, it's only spinning at 500 miles per hour, but it's spinning at over 1,000 miles per hour at the equator. This difference is what causes low pressure systems to form counterclockwise rotations in the north and clockwise in the south because of the shear, which is impossible, but that's for another video. So let's get into this and see if there's exceptions to the rule, because if there is, Coriolis is not causing low pressure systems to spin the way they do in their respective hemispheres. Heat expanding away from the equator in different directions causes the usual, but not always, rotations we see on the Earth. We're now going to look and see how cold air acts as a boundary. Remember boundaries. This will come in later as we look at fluid dynamics. All right, what we can see here is cold air coming in. Cold air is a blocking mechanism. Warm air goes to infiltrate it. It can't for the most part, and it starts to rise. Notice it gets a curve on it. When it hits a boundary, it starts to spin. This is important. Now, if the cold air was coming from the other way, the spin would be counterclockwise, where it's clockwise on this side with advancing cold air. Hopefully that's clear. No matter what your concept of the shape of the Earth, everybody knows that the sun more or less stays in the equator region of the Earth all through the year. And so we have the warmest air temperatures always being generated near the equator, as is diagrammed here. Now what this causes is this red area, a warmer, constantly heated more area than the rest of the Earth. Low pressure is created as warm air expands away from an area. Above that, relatively speaking, and below it, you have colder air, which is also higher pressure, or a high pressure area, as you can see here. What happens is, in fluid dynamics, the higher pressure area will flow into the lower pressure area in order to stabilize it, or try to equalize out the pressure. So you have an outflow generally from the equator towards the poles. And if you have an observer, in this case facing west, you would say the high pressure area from the equatorial region, which is also, as we discovered, the boundary area, is to the right of the equator when looking north, and to the left of the equator when looking south. It doesn't matter if the person is looking the other direction either. The boundary is going to be on the opposite side from where the low pressure area is located. Now the following video is very important. We're going to see about a minute of this. All this is doing is explaining part of air fluid dynamics. Air fluid dynamics is basically the same with some minor exceptions. What you're going to see here is pay attention to both laminar, which doesn't exist in our atmosphere, and turbulence. Laminar flow, turbulent flow. We have turbulent flow in our atmosphere.
Let's start with the walls parallel. Notice how the velocity drops sharply near the wall, and in this region the particles slide evenly over each other. This low velocity region is called a laminar boundary layer. Now let's open up the diffuser to a total angle of about 7 degrees. The increasing area of the passage causes the velocity to decrease and the pressure to rise in the direction of flow. Watch a streak square in the middle of the passage. You can see the deceleration. Also notice the flow near the wall. You see a thicker boundary layer now, and it is no longer steady. Instead, you see irregular, time-dependent eddies. This kind of boundary layer is called turbulent. Even though some of the particles very near the wall do not have enough momentum to overcome the rising pressure, they mix with the particles farther from the wall and are given sufficient momentum to keep moving in the downstream direction.
Now let's look at this again. So when he opens up the angle, it creates higher pressure at the end, and a boundary is to the left of the flow. Just like in North America, the boundary is to the left or the right, depending on your perspective, but it's the opposite south of the equator. The cold air is north of the equator in the northern hemisphere and south of the equator in the southern hemisphere. And I'm using their terms because their model will get rid of Coriolis force, because this is an exception to the rule, and you should be having no exception to the rule. I want you to notice these areas out in here and these eddies near the boundary. For the most part, they will spin counterclockwise up here and clockwise down here, all along the boundary. And when it escapes the boundary, when it really gets to expand, let's take a look. See that? Look up here, counterclockwise. Look down here, clockwise flow. And you'll see for the most part it will do this all along the boundary and outside, but there are a few exceptions. You can catch them, but it's rare. So here's another good spiral at the top and the bottom. Very plain to see. See the counterclockwise eddies up here and the clockwise down here. Every now and then you'll catch one. If you watch this video, you'll catch one going the wrong direction, but it's rare. This is how it works. There you have it. In rare cases, the colder air may not always be to the north in the northern hemisphere and might not always be to the south in the southern hemisphere. There are exceptions. There are cold fronts that move north in the northern hemisphere and vice versa in the southern hemisphere. Cold air retreats. Warm air sometimes tucks under cold air in an odd position. This is what causes exceptions. In my next video on Coriolis, I'm going to show both low pressure systems on a satellite map that are exceptions to the rule, and a tornado that is an exception to the rule. That is absolute proof that it is not faster air or faster earth at the equator. There would be no exceptions if that is what caused it, because it's always faster at the equator. Thank you.